Welcome back. Anomet is here. In this video, I'll be trying to dive a little in the operating systems, and the first thing that I wanna talk about is actually I wanna first ask again the question that we have asked earlier on in the previous video, which is how is the processor um, executing a lot of processes at the same time? This is the question that we have asked, and maybe it's time just to answer this question and at least have an idea on how is the processor is doing this. So let's just say now you are trying to, for example, build your own operating system, and I'm going to choose the path of a builder or someone who is trying to build something because to understand how a system like the operating system, or for example, to answer questions such as how are we executing a lot of processes at the same time, we have to take the place of a builder just to understand how this is happening exactly. So let's say you are building an operating system and you want users to be able to run multiple programs at once. You don't have actually a multi-core processor like yours that you have now in your computer, but let's say your CPU can only run one instruction at a time. So let's say you are lucky and you are a very smart operating system designer or developer, and you figure out that you can, for example, um, fake parallelism, which is the fact that you can let multiple processes take turns on the CPU. So if you cycle through the processes and run a couple instructions from each one, then they can all be responsive without any single process hanging on the CPU. But how do you take control back from a program code just to switch processes? And just after a bit of research that I did on the internet, and you should be doing that too if you want, you will be just discovering that most computers game with timer chips. So timer chips um, are like hardware devices or hardware components on your motherboard that can let the processor, um, like for example, fix something called time slices. I just love calling them time slices because there is another word we've been using in colleges to call this fact. Don't worry about that. We'll be back to that. So you can program a timer chip to trigger a switch to an operating system interrupt handler and just after a certain amount of time passes. So a timer chip can be programmed. So maybe it is time to talk a little about hardware interrupts now. Hardware interrupts, since I have earlier on talked about, so we talked about how software interrupts, which are in the previous video, are used to hand control from a user land program to the operating system. So these are called software interrupts because they are just triggering or they are just triggered by a program. So I think the majority of these software interrupts are triggered by the program's machine code, and the machine code is executed by the processor in the normal fetch execute cycle that we have talked about earlier on in the previous video that tells exactly the control to take control of the whole program at this point. What does this mean? Um, that means actually that when you do a software interrupt, you actually like saying to the kernel, "Hey, could you please take control from this point?" And the kernel should be responding to that. And the hardware interrupts actually, um, it's kind of the same, but it's actually uh, this interrupt is triggered by a hardware device. For example, when you plug in your mouse into your computer, that's called a hardware interrupt. When you, for example, plug in a, I don't know, a keyboard or anything into your computer, you actually do a hardware interrupt. So that's why the operating system scheduler, which is a fancy thing, uses timer chips like, for example, the PITs. So we can just Google the PITs. PITs are just a point in time readers. So they are used just to trigger hardware interrupts for multitasking and just, for example, before jumping to a program code. Uh, Wait a second, guys, before just complete, just explaining to you what the PIT is and the hardware interrupts. Don't forget to take notes because notes are necessary just when watching these kind of videos that I will be making before just diving into practice. Before we dive into more reverse engineering in the next videos, don't forget to take notes from the previous video and this video and the next video too. Yeah, because mainly if you don't take notes, you won't get a thing. You have to remember some stuff in the next videos too. So don't forget to take notes. Yeah. So before jumping to program code, um, the operating system will be setting the timer chip to trigger an interrupt after some period of time. So the timer chip will be programmed to be triggering an interrupt after some period of time, and the operating system will be switching from user mode and will be jumping to the next instruction of the program. And then, when the timer elapses, it triggers a hardware interrupt to switch back to the kernel mode and jump to the operation system code. And then the operation system code can now save where the program left off, and then load a different program and repeat, I think, the process. So basically, the timer chip will help us make the processor jumps between the user land programs and um, the kernel code or the operating system code. So this is called a preemptive multitasking. We have been learning this in college, and none of my professors actually explained it this way. The majority of them like throwing it as a bunch of boards. Like, but none of them just explained that there is something called user land and there is something called kernel land and all of that. So I've been trying to research that on my own. So yeah. So the interruption of your process is called preemption. Like if you are just trying to read anything on the internet, or I don't know, you are browsing and listening to music at the same time in your machine, your very own computer is probably like following this exact cycle like thousands of times a second maybe. Yeah. So this is basically what is happening. So now let's go back to time slices. So a time slice is the duration an operating system schedule allows a process to run before preempting it. What does that mean? For example, you have a process 1, you have a process 2, and your CPU is trying to manage that. How he is going to manage that? He is going to manage that using time slices. So for example, he is going to give to the process 1, I don't know, 10 milliseconds. He is going to give the process 2 20 milliseconds or something. So basically he is trying to manage that. Your operating system is doing all of that. So a time slice is kind of the duration an operating system scheduler allows a process to run before just preempting it. And the simplest way to pick time slices is just to give every process the same time slice, which is a pretty easiest approach to solve such a problem. Perhaps, for example, in the 10 millisecond range and just cycle through tasks in order. So for example, if the P1 comes before the P2, then we start executing the process 1 before the process 2 and so on. So like this is called a fixed time slice, for example, round robin scheduling. We have learned that in college too, but none of them just okay said that there is a whole theory behind the computers and all of that. We had an isolated class where we don't learn anything, so that's why I have researched that on my own too. So, an aside, just fun joke behind all of that. Like, did you know like that the time slices are often called quantums? Like, the word been thrown at us in college like quantum. So none of the professors explain to us what is a quantum. So a quantum is actually a time slice. So now you do, and you can just I don't know impress your friends maybe. But like speaking of time slices, um, words, Linux kernels, for example, Linux kernels devs don't use the word quantum. They use the word jiffy, which is a time unit just to count fixed frequency timer tricks. Well, that's actually um, pretty interesting, but none of them actually explained that to us. But the jiffy is interesting, is an interesting word too. Yeah. So let's do a slight improvement to the fixed time slice scheduling now and pick a target latency. So the ideal longest time for a process to respond. So the target latency, guys, is actually the time it takes for a process to resume execution after being, for example, preempted. So assuming a reasonable number of processes, this is pretty hard just to visualize, but don't worry, I will be trying to um, explain that more using, for example, diagrams or something. So time slices are calculated just by defining this target latency by the total number of tasks. Um, I think this is better than just fixing time slices scheduling because it eliminates wasteful tasks switching with fewer processes. For example, let's say with a target latency of 15 milliseconds, let's say you have a target and 10 processes, for example, we can just give each process just 15 by 10, which is 1.5 milliseconds, just to run. We can do that. This is this is quite good. Like, for example, with only three processes, I don't know, with only three processes, it would take us like 5 milliseconds. I don't know, just time slices to to hit the target. So with the processes, it will take us 5 milliseconds to hit the target, while with 10 processes, it will take us 1.5 milliseconds just to run. So each process uh, in this situation will take 5 milliseconds, which is a longer time compared to this one. So that's why processes switching is, let's say, like from a perspective of computations, it will be taking a lot and a lot of time, which will be expensive, and because it requires saving just the entire state of the current program before just restoring a different one. So when you are trying to save the current um, when you are trying to save the current state of the program at that time and switch back to another state, actually that is expensive in terms of time and in terms of memory. Past like a certain point, I think the smaller the time slice can result in performance problems with processes switching too rapidly, because it's common to give the time slice duration a lower bound, which is like the minimum boundary something. But I think this is or this does not mean that the target latency will be exceeding when there are enough processes for the minimum boundary to take effect. So at the time, for example, of watching this video, for example, link schedule uses, for example, a target latency of 6 milliseconds, and a minimum, for example, boundary of 0.75 millisecond. So, for example, we can just I don't know, just draw this little diagram. Just for example, I'm trying to imagine a diagram. For example, a process one, process two, process two, process I don't know, three. Let's say for example, and then you will get process one again. Um, so the target latency is all of that. This is the target latency. Is actually the time from where we have stopped to the time when we are back. So this is the target latency, and let's say we are going to give a time slice of I don't know, of 2 milliseconds, and this is actually, let's say, the kernel scheduler. So like this is just a little idea of a naive dynamic like time slice round robin scheduling. So a round robin scheduling with this basic like time slice calculation is close to what most computers do nowadays. So it's still a bit naive, but like most operating systems tend to have more complex scheduler, which I don't know, take process priorities and deadlines and a lot of configurations and a lot of stuff into account. But like, I remember just reading about something that says like since the 2007, I think, Linux has used a scheduler called Completely Fair Scheduler. You can Google that. Completely fair scheduler. It's a pretty famous one actually, but you see it's since the 2007. Yeah, so the CFS I think does a bunch of very fancy computer things to prioritize tasks and divide up uh, CPU time. So it's actually using binary tree to do that. You can just read about it. I think I have just read a little about it, but it's using a binary tree to do that. So every time the operating system preempts a process, it needs to load the new program saved execution context, so including its memory environment. So this is accomplished actually by telling the CPU to use a different table, which is the mapping from virtual to physical addresses. So this is also the system that prevents programs from just accessing each other memory. Don't worry, I will be trying to explain that in the next video, what I will be trying to explain for myself paging again if I was like 2 years ago, like I've tried to explain paging for a kid. Don't worry. So this is basically now how your operating system or how your computer is dealing with a lot of processes right now while you are listening to my video, while you are, I don't know, listening to music maybe, while you are reading an article on the internet, browsing the internet. Like the whole stuff is done using something called a schedule. So the scheduler is an interesting thing. You can read about it, and the kernel, that is a code about the scheduler. You can check it out just by running scheduler in the Linux kernel. Actually, I think Linux is one of the few operating systems that is available for you since it's an open source. You can read the kernel code. You can just check it out. Just read it. Go. Right, kernel, Linux kernel. It's pretty easy. Linux kernel, GitHub. It's in front of you. You can read as much as you want. If you want to understand something, you can read about it. Yes. So I think like just a little point or I want to just talk about something that I have find online, which is like I need to remember that. So yes, so I think ancient operating systems, just including the classic Mac OS and versions of Windows, long just before the NT kernel of the Windows, used a predecessor just for preemptive multitasking. So rather just using the operating system or making the operating system decide when to preempt the programs themselves would choose like to say to the operating system, hey, we want to take some time or we are not finished or something like that. So they would trigger a software interrupt just to say, for example, I don't know, hey, you can let another program run now and stuff like that. So these explicit like haze were the only way for the operating system to regain control and switch to like the scheduled programs are a little bit dangerous, and we can just call them. Let me remember the word. Like I think they are called cooperative multitasking. Is it cooperative? Cooperative multi? Is it multitasking? I don't remember. Yes, I think it's also known as. Yes, this is this one. Yeah, you can just research on that too if you want. So, like, it has a couple of major flaws. Like, one thing is that it's malicious or just poorly designed programs can easily freeze the entire operating system, and it's like a nigh impossible to ensure temporal or I don't know how to explain the word specifically, but uh, it will be just freezing the real time, which is a bad thing, I think. So for these reasons, the tech world switched to the preemptive multitasking, which is a long time ago and never looked back on that again. So yeah, this is the end of the video. I think if you had any kind of question, don't forget to ask in the comments section below, and don't forget to subscribe, and bye.